So it's my pleasure to introduce the last speaker on our seminar, Anzor Beridze of Batumi State University, also second affiliation at Kutaisi International University. And it is fit to have this last meeting on this topic, which is always present in Georgian topology over generations. And title being an axiomatic characterization of homology theory for general topological spaces. And so stage is yours, Anzor. So
thank you. First of all, thank you for organizing such nice seminar and to give me the opportunity to give this talk. So this is a joint, based on the joint work with Professor Baladze and Professor Tsinarishvili. And I will speak about the history, a small history, about the exact homology theory. I will pay attention this word. And first such kind of exact homology theory was defined by Steenrod. Before there was some papers, but Steenrod's paper is more popular, and this homology theory is called Steenrod homology theory, classical Steenrod homology theory. But at this time, the axiomatic characterization of this homology theory is not given, and this is done by the Milnor. And it is interesting that Milnor constructed exact homology theory on the category of compact Hausdorff spaces. And Steenrod's homology theory was constructed only compact metric topological spaces. So Milnor somehow generalized this homology theory and gave the axiomatic characterization of this homology theory. There are several statements, but I will pay attention modified continuity property. This is equivalent about additivity axiom of Milnor homology theory, but I will formulate this property because I need to pay attention to this property. What does it mean? It means that if we have the inverse sequence of compact metric topological spaces, and if we consider the inverse limit of this sequence, then homology of the limit space is connected to inverse limit of this homology theory of given topological spaces, and this is not isomorphic. If this is isomorphic, then we will say that this homology is continuous, but this is not isomorphic, but somehow we can control this homomorphism using the first derivative functor of inverse limit. And this sequence is called now Milnor short exact sequence. Somehow this formula was given in Steenrod's paper as well. But in this Steenrod's paper, this one is not written as an inverse limit, and it is called weak homology, somehow like that. So somehow this exact sequence was known for Steenrod, but Milnor gave this formula using the first derivative limit, and he proved that if homology theory satisfies this property, and this is called modified continuity property, then this is unique. This is very important result. And after that, there was the several papers given by several authors. For example, Kolmogov's paper was related to exact homology theory. And this is before the Milnor, but it was defined only the case when coefficient group is a compact topological group. And Chogoshvili's homology theory is exact homology theory. Sitnikov's and Borel-Moore and Inasaridze's and Edwards and Hastings. And Massey defined exact homology theory on the category of locally compact topological spaces, but here the mappings are proper mappings, and somehow this is a second type of homology theory, as Kliarenko says, such kind of homology theory. And there was a lot of papers, but all these homologies on the category of compact metric spaces coincides Steenrod homology theory. And axiomatic characterization, as I mentioned, was given for only compact metric spaces. And for compact topological spaces, first axiomatic characterization given by Beridze. And this was, the first paper was published in 1980. And recently, there was second paper, Inasaridze and Zinarishvili's paper, and it was given another axiomatic characterization of exact homology theory on the category of compact topological spaces. Later, there are Zinarishvili's paper and Inasaridze's paper, and there are again another axiomatic characterization. This was a little later, and it is very important that Inasaridze used the injective abelian group. If coefficient group is injective, then we have not only modified continuity property, but just a continuous property, and this is enough to prove the exactness theory of uniqueness theorem of exact homology theory. And for paracompact topological spaces, Beridze generalized Beridze approach. And what was this approach? I will pay attention later. But in our paper, what is our aim? We need to generalize this result for general topological spaces, not only compact topological spaces, but general topological spaces. But to do this, it's very important to modify cohomology, Alexander Spanier's cohomology. And this modification was done, really it was done by Morita, because Morita defined Alexandrov-Czech normal cohomology. Why it is the word normal? Because this cohomology is based on the normal coverings, not all open coverings, but only normal coverings. And if we do the same approach for Alexander-Spanier cohomology, then we will obtain Alexander-Spanier normal cohomology. But this is not new one, because we will prove that this cohomology and Morita cohomology is isomorphic. And we need this isomorphism to prove the uniqueness theorem of exact homology theory. And then after this cohomology, after constructing this cohomology, we need somehow to construct homology theory which is connected with Alexander-Spanier normal cohomology theory using the universal coefficient formula. But problem is here, because this cohomology theory is not defined by free cochain complexes. Cochain complex is non-free. And if cochain complex is non-free, then to write down universal coefficient formula is a little difficult. And so we developed this method in our paper with Professor Zinarishvili. We have joint work. It is not it's unpublished yet. It is archived, but it is submitted to publish. And using this approach, we construct so-called Alexander-Spanier normal homology theory. And this normal homology theory is constructed for general topological spaces. And we have axiomatic characterization of such kind of homology theory on this category. And as I mentioned, this talk is based on the joint works with Professor Baladze and Professor Zinarishvili. Now, maybe it is not necessary to recall what's the homology functor and cohomology functor, because I think everyone knows this notation.
I think it's still good if you spend a couple minutes on that, because yeah, it's going to be recorded. It is recorded, and not all in the audience are topologists. Just
okay. Let's take that category of pair of topological spaces, and we need some property to construct a homology theory on this category. This is called admissible subcategory of this category. And let's take the category of abelian groups. And if we take the sequence, such kind of sequence of abelian groups, where for each n, Hn is a covariant factor from our category to abelian group, category of abelian group, then such kind of sequence is called homological functor if we have the following: for each pair of topological space, and for each abelian group, and for each integer, we have the delta homomorphism. It is called connected homomorphism, which decrease the dimension of this homology groups. And if we have the continuous map from one pair to the another, then we have induced homomorphism, of course, and induced homomorphism and this delta homomorphism gives such kind of commutative diagram. And if we have the homological functor, then we will say that this homological functor is a homology theory if it satisfies homotopy, excision, exactness, and dimension axiom. So problem is exactness in the case when we have the homology theory. What about cohomology? Cohomology is the same approach, but we have contravariant functors, and we have a sequence of contravariant functors, and we have these properties. And if we have these axioms, then we will say that this cohomological functor is a cohomology theory. So cohomology theory, I will say, is Steenrod-Eilenberg sense, because this axiom characterizes homology and cohomology theory on the category of compact polyhedral spaces. But what does it mean that this axiom characterizes the homology and cohomology theory of compact polyhedral spaces? If we have two different homology theory on the category of pair of compact polyhedral spaces, and if both are theory, satisfies all axioms, then for each coefficient group, we have unique such kind of homology theory. We cannot construct two different homology theory if coefficient groups are the isomorphic. And the same happens about the cohomology. And so Steenrod-Eilenberg's axiom characterize homology and cohomology theory on the category of compact, on the category of pair of compact polyhedral spaces. And that's why the first approach to characterize the cohomology or homology, more general category, was given in several papers. And one of them is the continuous property for cohomology. What does it mean, continuous property for cohomology? And category is pair of compact topological spaces. If pair of topological spaces is inverse limit of compact polyhedral, so it is always possible to construct compact topological space as an inverse limit of compact polyhedra, then we have such kind of isomorphism for Alexander-Spanier cohomology or Czech cohomology. And if we have such kind of isomorphism, such kind of cohomology is a unique. So if we add this property for cohomology on the category of compact topological spaces, this isomorphism characterize the cohomology. on the category of compact topological spaces. So it is quite large category than compact polyhedra. This is very good result, but such kind of isomorphism cannot written for homology. And Milnor's first approach was this one, but this was done for not compact topological spaces, but compact metric topological spaces, on the category of compact metric topological spaces. So here, any compact metric topological spaces can be considered as an inverse limit of inverse sequence. Not inverse system, but inverse, even inverse sequence. And if we consider the limit space, the Steenrod homology theory of limit space and the limit of Steenrod's homology groups of each such kind of topological spaces is connected by this short exact sequence. So this is not isomorphism, but we can control this, this homomorphism using the first derivative limit of these groups. And this was done by Milnor. But again, this was done only for compact metric topological spaces. And somehow this is equivalent to additivity axiom and as we call sometimes wedge axiom and strong excision axiom. And so this is enough to prove the uniqueness theorem for homology theory. And that's why Steenrod's homology theory, because Steenrod homology theory satisfies this axiom, and because almost all exact homology theory satisfies this axiom, all of them, they are isomorphic on this category. And this is a result that homology theory defined on this category, which satisfies Steenrod-Eilenberg's axioms and modified continuity, which means that we have such kind of short exact sequence, then this is isomorphic to Steenrod's homology theory. It is not formulated in Milnor's paper exactly like that, but this is equivalent to this statement. The important is the following, that Milnor, as I mentioned, Milnor constructed new homology theory on the category of compact topological spaces, not only compact metric topological spaces, but compact topological spaces. The formula Milnor short exact sequence was given only compact metric topological spaces, but universal coefficient formula was given for compact topological spaces. Here is a maybe Czech's cohomology or maybe Alexander Spanier's, does not matter, they are isomorphic. And this formula was known by Milnor, but Milnor did not prove that this is enough to prove uniqueness theorem on this category. And first such kind of theorem appears in Berikashvili's paper, and Berikashvili proved that if we have any homology theory, it does not matter here is a Steenrod's or any other homology theory, for which we have universal coefficient formula. In Berikashvili's paper, he's a Czech's cohomology, but this is a isomorphic, does not matter. Then such kind of homology theory is unique. And this was first uniqueness theorem on the category of compact topological space without metric. And recently, the second uniqueness theorem was given by Inasaridze and Zinarishvili. And the Milnor short exact sequence is given now on the category of compact topological spaces. By Milnor, this formula was known only compact metric topological spaces. And in this paper, it is done for any compact topological spaces. And here essentially is that this group size finitely generated, and we don't have second derivative limits and high derivative limits. And this is very important restriction when we have the compact topological spaces. And it is proved that this short exact sequence is enough to prove uniqueness homology theory. Any homology theory which satisfies this formula is unique on the category of compact topological spaces. And later, Anzor Beridze gave another axiomatic characterization. Here is isomorphism, as it means that this first derivative must be 0, but not all coefficient group, but this coefficient group must be injective abelian group. And when this coefficient group is an injective abelian group, then derivative is definitely 0, first derivative limit, and we will obtain the isomorphism. And this isomorphism only for injective abelian group is enough to prove uniqueness theorem, but homology theorem must be bifunctor. This must be functor with respect to coefficient group, but this is not big restriction because any homology theory is a bifunctor, and so Anzor Beridze obtained uniqueness theorem for exact homology theory. And now, what we need and what is a problem and what we solved after that. All this case, when topological space is a compact topological space, it is possible to construct free cochain complex. Those cohomology, free cochain complex, those cohomologies are isomorphic to Czech's cohomology. And this is big advantage. Those cohomology is isomorphic to Spanish cohomology or Czech's cohomology, it does not matter, of topological space. So cohomology of topological space, if topological space is compact, is possible to construct such that we have free cochain complex. And if we have free cochain complex, then it's very easy to write down, of course, a universal coefficient formula. And then we can follow maybe Berikashvili's approach, maybe Zinarishvili's and Anzor Beridze's approach, and we can prove the uniqueness theorem. But problem is the following: when this cochain complex is non-free cochain complex, and if coefficient group is non-injective, then we have some problem. But if we consider the injective resolution of this group, or maybe this is module, but on the principal ideal domain, we need the short injective resolution, then we will obtain the G prime, from G prime to G2 prime, the homomorphism beta. And this homomorphism induce the chain homomorphism between home group, home defined by G prime, to home defined by G2 prime. So instead of this group, I will pay attention the induced homomorphism by beta between chain complexes. And this chain complex has, of course, chain cone. And somehow, using the group of any abelian group G, somehow we construct chain complex. And it is given how to construct this chain group. This is a standard definition of cone. And somehow we have the chain complex. And if we have chain complex, then homology group of this chain complex, it is written homology of cochain. But what does it mean, homology of cochain complex? Homology of cochain complex means that using of this cochain complex and using this group, we have constructed chain complex, and this is a homology of this chain complex. That is, a chain complex is a chain cone of chain map. And somehow we can construct homology theory. And for this homology theory, we have universal coefficient formula. And interesting history is the following, that And we have the joint paper with Zinarishvili, and we have investigated this property. But this is not new result. This result was known before. This result was known by Spanier, and this result is mentioned in the paper of Zinarishvili and Spanier's paper. But it is done for dual version of this one. But at least we did not know the proof of this universal coefficient formula. But we have done this one. As I mentioned, this is not a new result, but this is essential for our case because cochain complex is non-free, and somehow we construct homology theory of this cochain complex such that we have universal coefficient formula. Here are the cohomology groups, and here is a homology groups, and we have universal coefficient formula. Standard case, this formula is valid for cohomology theory. But as I mentioned, this kind of formula was known by Milnor and by Berikashvili. It's proved that this formula is enough to prove uniqueness theorem on the category of compact topological spaces. And using this universal coefficient formula, we have proved this following theorem. And this result is almost dual of the result of the Zinarishvili and Spanier's result. What does it mean? If we have the direct system of cochain complexes, it does not matter these cochain complexes are free or not. Even these cochain complexes are free, maybe limit is not free, maybe problem is again arised. But in our case, any inverse limit of cochain complexes, we have such kind of long exact sequence. This is a very essential long exact sequence because this is generalization of Milnor short exact sequence. If we write 0 here, and if we write 0 here, then this will be Milnor short exact sequence. So in the case of compact topological spaces, this derivative limits was 0 because cohomology groups was finitely generated, and this gives this result. But in general case, when we work non-compact topological spaces, maybe we have high derivative limits. And this is done here. Such kind of formula was done by Zinarishvili and Spanier in the dual version of this one. But we have done, when we have the cochain complexes, using the cochain complex, we will construct a limit cochain complex. Using this cochain complex, somehow we can construct the chain complex that is a cone of cochain map, and we will obtain the homology. And for such kind of homology, we have long exact sequence. And this is a very important result to prove uniqueness theorem for general topological spaces. Now, I mentioned that somehow we construct Alexander-Spanier normal cohomology theory. And everything is a standard. Here is nothing new, except that we have considered the normal coverings. Not all open coverings, but normal coverings. Coverings such that there exists a partition of unity that is subordinated on this covering. And this approach is very popular in shape theory, and resolution in shape theory is constructed using not all open coverings, but all normal numerical, so-called numerical coverings. And this is important because for cohomology theory, continuous property was valid on the compact topological spaces. But if we construct a little modification, if we do a little modification of Alexander-Spanier's cohomology, and if we restrict coverings by normal coverings, then this cohomology theory will be much interesting because Watanabe has proved continuous property for general topological spaces, and I will say what does it means. And as I mentioned, this theory was constructed by us, but this is not a new one because this is isomorphic to Watanabe's cohomology theory. And this is very essential, this isomorphism for us. And here is an important bridge is Dauker's lemma, which connects the nerves and Vietoris's homology theory. It works well here. It is not a problem at all, but what is the advantage of our cochain complexes? So we can consider the short exact sequence of cochain complexes of pair any topological spaces, but such A must be P embedded. This is well-known restriction. We need this restriction, but we don't have restriction on the X. And using our approach, as I mentioned, this is a cone of chain mapping, not home of this cochain complex. We will construct the exact short exact sequence of chain complexes. And of course, homology theory of these chain complexes gives the exact homology theory. And this homology theory is called Alexander-Spanier normal homology. But what is the main result for this homology? For this homology, we have proved universal coefficient formula is valid. What does it mean? If we consider any pair of topological spaces and homology theory defined by us, maybe here it needs the N, normal, Alexander-Spanier normal homology theory, then we have the universal coefficient formula. This formula was known only compact topological spaces. Now it is valid for any topological spaces, but construction of this homology theory is somehow different. As I mentioned, we use the resolution, injective resolution of coefficient group, and using this resolution, we somehow constructed chain complex, and homology of this chain complex is Alexander-Spanier normal cohomology. And this is one property. Second property is the following, that if we take pair of topological spaces, and resolution in sense of shape theory. Of course, not every inverse limit is resolution, but on the compact topological spaces, resolution and inverse limit is the same. But if we take a resolution of this pair, maybe not inverse limit, this result is not valid, but if we take resolution here, then we have such kind of long exact sequence. What does it mean? If this is a 0 and this is a 0, then remaining part will be Milnor short exact sequence. And this is true for compact topological spaces, but in general topological spaces, we need high derivatives as well. So this is generalization of Milnor short exact sequence. And why I consider the resolution and not inverse limit? Because for Watanabe cohomology theory, that is constructed by normal covariance, this isomorphism is proved by Watanabe. This is a maybe Morita cohomology, but it is proved by Watanabe that cohomology of topological spaces is isomorphism of inverse limit of cohomology of these spaces. What is the X alpha? These X alpha are spaces from resolution. So Watanabe mentioned and Watanabe gave the example that this isomorphism is not valid for inverse limit, but inverse limit must be replaced by resolution. And for resolution, of course, for compact topological spaces, they are absolutely same, but for general topological spaces, it must be resolution. That's why we consider resolution and we obtain such kind of long exact sequence for resolution. And even more, this is like a Zinarishvili and Inasaridze's axiom, and this is like a Inasaridze's axiom. If we take a resolution again, and if we take injective abelian group G, then we have such kind of isomorphism. And this three property is valid for our homology theory. And there are very good connection between these properties. But the last one is absolutely enough to prove uniqueness theory. Because if we have the first one, then we have second one. And if we have second property, we have the third property. And if we have the third property, this is a continuity for injective group. Then we have uniqueness theorem in general topological spaces. And we have, but this functor, this homology must be bifunctor as well as in the Inasaridze's case. If we have the bifunctor defined on the category of topological spaces, which satisfies universal coefficient formula, but it is enough to consider this universal coefficient formula only polyhedral pairs. Then we can prove that this will be valid for general topological spaces. And if Eilenberg-Steenrod axiom is valid on this subcategory, if this is a valid on this subcategory, then everything will be valid on the general category. And if we have this property, this isomorphism, but only injective abelian groups, then this homology theory is a unique. And this is a joint paper with Baladze and Zinarishvili. And maybe I have 10 minutes and I will review some remarks
you
about—
sure have 10 minutes, yes.
Yeah,
More than 10 minutes.
About the proof. I will mention the main formulas and main approaches, and I think that it's enough to say for this homology theory. So somehow using the normal covering, somehow it is possible to construct inverse system. And using this inverse system, Mardejic has constructed resolution. But for us, it's enough to construct such kind of inverse system. Each topological space is the geometrical realization of nerve of covering. And here, P lambda prime is uniquely defined. And this is a Mardejic's approach how to construct such kind of mapping such that this is an inverse system. But this is not new. We use this property and somehow we have such kind of mapping from topological space to this inverse system. And each topological space is defined by normal covering. This is a nerve and its geometrical realization, and this is uniquely defined. It is possible to do like that using the shape theory. And using this inverse system, I will consider the inverse limit. And essential is the following. Because we have the bifunctor, for any abelian topological, any abelian group, I will consider the injective resolution. And this injective resolution gives the long exact sequence of homology theory. Here is an injective, here is an injective, here is an injective. This is not injective, but for injective group, we have isomorphisms. And so for non-injective group, we will obtain that this is isomorphism as well. So for any topological space, homology group of this topological space and homology group of this limit space is isomorphic. For paracompact spaces, these spaces are homotopy equivalent as it is mentioned in Anzor Beridze's paper. Here, X and this limit is not homotopical equivalent, but homology theories are isomorphic. This is not easy proof, but main trick is here. So after this isomorphism, I can consider the filtration of this space. What is this filtration? For any n, I will consider the skeleton, n-dimensional skeleton. This space is geometrical realization of the nerve without n, so it has the skeleton, and so we can construct filtration. And the first essential formula is that for cohomology, we have such kind of isomorphism. For cohomology, it is a little easier to prove. But for homology, we have universal coefficient formula. And here is cohomology. And this cohomology is direct limit of cohomology of polyhedral space. But unfortunately, this polyhedral space is not compact polyhedral. So we cannot say that it is enough to consider the limit of cohomology of polyhedral spaces. But fortunately, cohomology of these non-compact polyhedral spaces can be connected cohomology of compact polyhedral spaces. This is subspace of this one. All possible compact subspaces. It is connected to compact polyhedral cohomology of compact polyhedral spaces and its limit and inverse. It is controlled by first derivative limit. And this formula was done by Zinarishvili for singular cohomology. It was published in 2018. And we have the joint paper. It is published in topology and its application about the axiomatic characterization of singular cohomology theory. This is the similar as a compact support for singular homology theory, but this is very essential. This is like a Milnor short exact sequence, but not homology, but cohomology. And so these three formula is absolutely enough to prove uniqueness theorem. Why? Because if we start for topological space, homology theory of this topological space is isomorphic of homology theory of this limit space. And I need to calculate the homology of this limit space. But I will consider the filtration and cohomology. I know cohomology of filtration, but homology of this filtration is connected with cohomology of this filtration. And this cohomology of this filtration is limit of cohomology of polyhedral spaces. And cohomology of these polyhedral spaces can be connected cohomology of compact polyhedral spaces. And for compact polyhedral spaces, we have uniqueness theorem. And somehow it is possible to prove. What is the main result? For our homology theory, if we consider our filtration, this is 0. And this is standard isomorphism in Steenrod-Eilenberg's uniqueness theorem. If this is a compact polyhedra, and if we consider the n-dimensional skeleton, then this is valid. And for such kind of pair, in standard case, this must be 0 even when P is equal to n-1. But problem is exactly this, that this homology theory is not 0 if coefficient group is not injective. But fortunately, if coefficient group is injective, then we have such kind of isomorphism as well, but not general abelian group. And this is a standard approach. I will construct the chain complex using this homology theory. What is an n-dimensional chain complex? N-dimensional chain complex is n-dimensional homology of this pair. But I can do this only injective coefficient group, because for non-injective coefficient group, I don't know this is 0 or not. But for injective group, I can construct a chain complex. And of course, I can construct using the connective homomorphism, this delta homomorphism, and this is a chain complex. And essential is that homology group of this pair can be written as a hom of limit of cohomology. So it does not depend on the homology. It depends only the cohomology. So it means that this chain complex is independent of choice of homology theory. But everything up to now is done only injective abelian groups. And what's happened? Non-injective abelian groups. This is a chain complex for injective abelian group G prime. This is a chain complex for injective abelian group G2 prime, and we have the homomorphism. And if we consider this homomorphism as a chain map of these chain complexes, then I can construct the chain cone of this chain complex. And fortunately, homology group of this chain cone is definitely homology of this limit space. And homology of this limit space is homology of our topological space. This is a main approach, and that's why this is valid for general topological spaces. And if we have the category of paracompact spaces, as I mentioned, in this case, we don't need continuous property with respect to injective abelian group. It is enough to have universal coefficient formula, and this was done by the Inasaris on this category, because this limit space and given space is homotopical equivalent. So I have something more, but I will finish here. Thank you.
You're done. Thank you so much. So I now stop recording.